Chapter 13, we're going to take a look at sound. Sound waves, first of all, are longitudinal waves. They're produced by vibrations that compress and rarefy the air, squish it together, or spread the particles out in the medium through which it's traveling. Sound waves are also mechanical waves. Remember, mechanical waves are waves that need a medium to travel from source to detector. Sound waves cannot travel through a vacuum. Also, sound waves are three-dimensional, and they can travel in all directions. If you remember from the wave labs that you did already, we looked at two-dimensional waves. They traveled along a slinky, or they traveled along the surface of the water. Sound waves can travel in three dimensions, so they can travel up and down, front and back, left and right. And so rather than thinking about a wave front as a line, we think about a wave front as the surface of a sphere. Because sound waves are mechanical waves, the speed of sound depends on the medium. As the density increases, the speed increases. Related to sound is the term pitch. And pitch is defined for us as the subjective interpretation of frequency. The frequency doesn't change, but the pitch may, depending on how it's perceived. The next thing we're going to take a look at is something called beats. And beats is what you hear when you have two simultaneous frequencies played. The frequencies are different. So that's the definition of beats. Let's take a look, first of all, and see what they look like. And in class, we'll be able to hear what they sound like. So if we look at the top row, we have a frequency of N, and it's 10 cycles per unit of time. So we can say 10 hertz if our unit of time is seconds. The green one is a second frequency higher. It is 12 cycles per second, or if we say cycles are hertz, then it's 12 hertz. And if we superimpose one over the other, what we'll see is there are some places where the troughs line up. So here and here the troughs line up. There's some places where the trough of the green wave lines up with the crest of the blue wave. So here and here and here. And when that happens, what we hear is what is shown in the red. So where the troughs are aligned, we have constructive interference, and so the sound is louder. Where the trough of one aligns with the crest of another, we have destructive interference here and here and here, and the sound is much softer. So what you hear is a loud, soft pulsing of the sound. So we can see what this looks like. Here's a similar diagram, but let's put it into action. So here we have the white wave on top, has a frequency of 14 hertz. The green wave in the middle has a frequency of 16 hertz. And it says that they're in phase. That means that they start and both of them are going towards the trough portion of the wave. So let's start and see what it looks like. The orange pattern at the bottom shows us what the combined sound waves sound like. So we're following the blue bouncing ball, and as we have troughs line up, we get an amplification of sound. As we have the crest and the trough aligning, we have a dampening of sound. So loud and soft alternation is what we hear. Again, we'll take a listen to this in the classroom to hear what it sounds like, in addition to now seeing what the pattern looks like. The next thing we're going to take a look at is intensity. Intensity is the rate of energy flow at the wave front. So if we look at the diagram to the right, our sound source is right here in the middle, and as time goes on, our sound wave moves and the wavefront gets larger and larger as it moves away from the source. So if we take a look at the squares, surface area here, as we double the distance, becomes 4 times larger. When we triple the distance, it becomes 9 times larger. And so it's an inverse square relationship. We've seen inverse square relationships before when we talked about Coulomb's law and forces. The equation for intensity looks like this. It is the change in energy per unit of time over the surface area of the wavefront. So change in energy over time is power. Surface area of a sphere is 4 pi r squared. So we can calculate what the intensity of a sound is if we know the power output of the sound source and if we know our distance from the sound source. That would be the radius. Something called the threshold intensity is the softest sound that humans can detect. And people have put a numerical quantity on this. I sub 0 is 1.0 times 10 to the negative 12 watts per meter squared. So it's a pretty tiny number. Relative intensity gives us a scale of intensity of our sound compared to threshold intensity. And so relative intensity is the intensity divided by I0. And again, that gives us a ratio, but it's not terribly useful. It turns out that Alexander Graham Bell came up with a much more useful equation in a way to discuss how loud or intense sounds are, and he came up with a decibel scale. The symbol for decibels is beta, just like F is for force and M is for mass. Beta is for decibels, and the formula is 10 times the log of the relative intensity, so I over I0. And volume is related to the decibel scale, but not directly. It turns out that volume doubles for every 10 decibel increase. The units for decibel are dB, and on the right is a diagram showing a decibel scale. So the faintest sound that you can hear would be 0 on the decibel scale. We'll bring out the decibel meter in the classroom, and what we'll find is the decibel reading of the classroom is going to be somewhere between 50 and 75 decibels. It turns out when you get to 120, that essentially is potential for damage. So if you're subjected to sounds generally even above 110 decibels, it's a good idea to wear hearing protectors. If you're subjected to decibels over 120 for long periods of time, what will happen? It will damage your hearing. Let's work through a decibel problem just to make sure we know how to solve these problems. So we're going to take iPhone and earbuds, and I looked online, and what I found is that the average power output is 60 milliwatts. And if you're listening to your favorite songs and your earbuds are in, the distance between the earbud and your eardrum is about 1.5 centimeters. We're thinking we have really big ears here. So that's going to be your radius. First of all, let's find out what is the intensity of the sound that you're subjecting your eardrums to. So the intensity is going to be the power, 60 milliwatts, over surface area of a sphere. So we've got 4 pi r squared, so that's 0.015 meters. And what we find is we get an intensity of 21.22 watts per meter squared. Well, that doesn't seem to be like a very big number. Let's figure out what the decibel rating for that is. So we have 10 times the log of 21.22 over 1.0 times 10 to the negative 12. Well, now things get interesting because what we find is we have a decibel reading of 133 decibels. So if you have it cranked up full power, you're way beyond hearing damage levels. So you might want to rethink how loud you listen to your music. Either that or not have your earbuds in when you listen to it that loud.